Lesson 6.5, Graph Square Root Functions. Notice I've crossed off what was originally on this slide, and I wrote f of x equals square root x. That's an example of a square root function. I've also crossed off the equation y equals x on the right-hand side on the graph, but that line we can't get rid of, so we're just going to leave that there. As we think about making a table and sketching the graph of this function, we have to think about a restriction for x. So we are going to talk about domain in this lesson. Numbers that we can plug in for x, remember x is called the radicand of this square root function. So I'm going to use the term radicand quite a bit today. We want to figure out what values make that radicand possible and what values we can't pick. Anytime we try to plug in a square root for something, we have to have a positive number. Our goal in the table is to pick values over here that will give that square root meaning. I always like to start off with the smallest number possible and then work from there. The smallest number we can take the square root of is 0, because the square root of 0 is just 0. Now you can pick other numbers if you want and get decimal answers, or you can try to pick numbers that will give you integer or whole number solutions. 1 would be a good number to pick because the square root of 1 is just 1. 2 is fine to pick, but when you pick the square root of 2, it's approximately 1.4. So you may need a calculator if you want to do decimal approximations. But if you can think about perfect squares to plug in, you'll get whole number answers to graph. So I'm going to skip 3 and I'm going to go up to 4. The square root of 4 is exactly 2. So I'm getting nice numbers to work with on the graph. But then the next perfect square goes all the way up to 9. So that puts us to the edge of our graph on the right. And the square root of 9 is 3. Now over on the right, I'm just going to zoom my graph out so it's easy to see where these points are coming from. So if I plot, well, let's kind of even that out a little bit. If I plot the points on the left, I started with 0, 0, and I have 1, 1. They're not meant to be on this line. Again, the reflecting line doesn't need to be on there, so sorry about that. At 2, it's about 1.4, so then notice it kind of tapers off just a little bit. Square root of 4 goes up to 2, and then if we go all the way over to 9, it goes up to 3. So you can kind of see the graph starting to turn a little bit over to the right. So it doesn't go up like a linear function. Remember, a square root function is non-linear. Again, the other thing to note is that that start point at 0, 0, we don't go anywhere beyond that on that left-hand side. That would mean x is negative. To sketch this graph, you're just going to start at 0, 0 and draw a curve through those points with an arrow on the right-hand side. And that's an example of a square root parent function. As we think about what gives this function meaning, we're going to focus on domain again. For any square root function, we know that the number on the inside has to be greater than or equal to 0. Sometimes it's just x. So for this function, for example, we would just say x is greater than or equal to 0. But if you have a transformation or you move this around a little bit, for any other domain, you want to set the radicand, whatever is on the inside, greater than or equal to 0, and solve. That's if you move the equation around, and that will help you determine the new domain, which will also help you determine how to make your table. Let's take a look at graphing some radical functions. By definition, a radical function is just any function in the form y equals square root x. But we could also have f of x, we could have g of x, and so on. When we graph, we're just going to make our table and pick the first x value that makes the square root equal to 0. So we're going to look at that domain, and we're going to look at the radicand being greater than or equal to that 0 value. The first thing I'm going to do, however, is go to my graph, and I'm going to plot the parent function, the values that we used on that last page. And I'm only going to use the ones that were perfect squares, but you definitely can have decimals. There's nothing wrong with that. We plotted 0, 0, 1, 1. I'm going to skip the 2, and then we went 4 because the square root of 4 was 2. 9, the square root of 9 is 3. So over on the right, I'm just going to write y equals square root x. Again, this is called the parent function. Our goal is going to be to take a look at the new equation and describe and see how that changes from the shape of the parent function. The new equation is y equals negative 2 times the square root of x. Notice negative 2 is on the outside and the plane x is on the inside. So just x is the radicand, not the negative 2. Because of that, our domain is going to stay the same that it did on the first slide. As long as the number on the inside is greater than or equal to 0, we're in great shape to sketch our graph. And that number will also help us with our table. So when I make my table for x, I'm going to start with that domain value. That's always going to be where you want to start, the first value that makes the square root equal to 0. So if I plug in 0 for x, we have negative 2 times the square root of 0. Think order of operations, square root of 0 is just 0, and negative 2 times 0 is 0. So there's our output. The next number we plugged in for x was 1. That's another perfect square root answer. The square root of 1 is 1, and negative 2 times 1 actually becomes negative 2. Again, we're going to skip 2 just because that gives us a decimal, but if you want to type that in and get an output, you're welcome to do so. I'm going to jump up to 4 because that's a perfect square root again. The square root of 4 is 2, and negative 2 times 2 puts us all the way down to negative 4. If I go out one more to 9, that again is going to put us at the edge of our graph. Let's see what our output is there. Negative 2 times the square root of 9, well, the square root of 9 is 3, and negative 2 times 3 is negative 6. Let's plot these points to see how it looks different from our parent function. When you plot 0, 0, 1, negative 2, 4, negative 4, and 9, negative 6, we're starting at that same initial point from our table, and now the graph curves down through these points and ends over at that right-hand side. We're going to describe this transformation as it compares to the parent function. When we have a transformation, that coefficient out in front is the lead coefficient, so that's our a value. When there's a number out in front of x, it has an impact on our graph. If a is greater than 1, the graph stretches. So 2 is technically greater than 1. So our graph is going to stretch vertically because it's bigger than the parent function. Now the negative does something different. The negative out in front actually reflected the graph over the x-axis. And that's how you describe the shape from the parent function. So when I say reflects over the x-axis, that means it's going to open down instead of open up like the parent function did. So we have our domain, that's one part of our problem. We have our table, and we have our description. And of course, the graph itself. Let's take a look at the next square root function. Y equals square root x minus 3. You'll notice over on the right, I've already graphed, the parent function. Y equals square root x. Feel free to plot that and then press play to continue, and we'll show what happens with this new transformation. As we look in the inside, notice the radicand isn't just x. The radicand is x minus 3. When we determine our domain, which helps us determine our start point, we said by definition the radicand has to be greater than or equal to 0. Therefore, if I set x minus 3 greater than or equal to 0, we have to get x by itself. To do that, I'm simply going to add 3. And voila, there's your domain. X has to be greater than or equal to 3 to give this function meaning. And that's also going to be the number in our table. So remember that number that we calculate in the domain is always going to be our start number. If I start with 3, we have the square root of 3 minus 3, which would be 0, and the square root of 0 is 0. Now if I think about other numbers to plug in, notice it says greater than or equal to 3. So let's try to think of numbers that will give us a perfect square root answer. If I pick 4 and I plug that in, 4 minus 3 is 1, and that's a perfect square root. The square root of 1 is 1. But if I pick 5, 5 minus 3 is 2, and the square root of 2 isn't a perfect square. We can still graph it, but you have a decimal. So can you think of the next number that we could plug in so that we get a perfect square, or excuse me, a perfect square root? We have 0, we have 1. The next perfect square root would be 4. So we'd have to go all the way up to 7. Watch how this works. If I plug in 7 minus 3, there's the square root of 4. And the square root of 4 is 2. To get to the next one, that's a little trickier. The next perfect square is 9. But to get an answer that's the square root of 9, we have to go all the way up to 12. So we're going to have to go slightly off our graph for this next ordered pair. 12 minus 3 is 9. And the square root of 9 is 3. So we have 3, 0. I'm going to plot that point. We have 4, 1. We have 7, 2. And we have to go, oops, make that a little taller there. And we have to go all the way past 12 to get up to 3. So I'm just going to kind of approximate that over here on the right. Let's slide this over so we can see this sketch in a little more detail. Kind of even it out a little on the screen. Now if we connect those 4 points, the curve is actually going to be very similar to the original curve. Whoops, and I missed that last part right there. We're close enough. So that's y equals square root x minus 3. Notice the shape didn't change, we just moved the location. This is kind of like moving the vertex of a quadratic function way back in chapter 4. Can we describe what happened here? Remember, anything that was with x always moved left or right, but in the opposite direction? Notice it says x minus 3 on the inside, but because of the domain, the graph shifted 3 units to the right. So our description would just simply be moves right 3 units. And that's all the transformation did from the parent function. And there's our second transformation of a square root function. And then all of a sudden we get a function like this one. F of x equals negative square root x plus 2 minus 1. Let's see if we can describe this first before we make the graph. We have a negative on the outside. So that negative means it's going to reflect over the x-axis. So the curve will open down instead of up. Be kind of like the bottom part of it instead of the top part of it. So reflects over the x-axis. And then we have a radicand of x plus 2. Notice the minus 1 is after. So we're just going to move it left or right based on that radicand rule. And if it's x plus 2, we remember to move it 2 units to the left. So it's going to move left 2 units. And we'll be able to see that on our graph when we make our table. And then last but not least, remember anything that was after the x for quadratic functions moved up or down the same number. Since that value is negative, the whole graph will move down 1 unit. So that's just kind of a little refresher from way back in chapter 4 when we talked about quadratics. Let's see how we can use that to find our domain and to make our table. Remember, for the domain, the radicand itself has to be greater than or equal to 0, and that's just the inside of the square root. If I say x plus 2 has to be greater than or equal to 0, that would mean the domain is just x is greater than or equal to negative 2. And remember, that's the number we're going to use in our table. All right, technical difficulty for a moment. That text tap to edit button, I can't get that to leave my screen. So sorry, we're just going to have that on there for, visual effects, I suppose. All right, so we're going to start with negative 2. Now here's the thing, everybody. We've got to plug it into the original equation and then kind of work inside out to get our answer. And make sure that minus 1 is on the outside. If I start with the inside, though, negative 2 plus 2 is 0. So that gives me negative square root 0 minus 1. Well, square root of 0 is just 0. Negative 0, again, is just 0. So 0 minus 1 equals negative 1. Yikes. All right, so I'm going to kind of divvy this up so that I know where my input and output matches. So I'm going to go to another one. Let's see. We want to try to find values for x that make the inside a perfect square root. So if I go greater than -2, if I go to -1, let's see if we make that happen. If I plug in -1 on the inside, so we get -1 plus 2, and then -1 after. Just on the inside alone, -1 plus 2 is 1. So we're in good shape with that. Negative square root 1 minus 1. Well, the square root of 1 is 1. And -1 minus 1 is -2. So there's our output for that answer. Oh, so we can see how some of these are going to get kind of tricky. All right, let's continue on. We still want to get bigger than -2. What else could we plug in? What else will be the next one to make our inside a perfect square root? If it's x plus 2 and I go all the way over to 2, then on the inside we have 2 plus 2, which is 4. I almost wrote it too fast. So 2 plus 2 on the inside, and then we have that -1. Okay, so that's square root 4, or negative square root 4 minus 1. Square root 4 is 2. -2 minus 1 is -3. I hope you guys can get all this to fit on your paper. There should be enough room. All right. What else? So we have 1, or we have 0, we have 1, we have 4. We need 9. 9's the next number we need on the inside. So what number plus 2 equals 9? We're going to have to go all the way over to 7. If I type in square root, or negative square root, 7 plus 2 minus 1. That's negative square root 9 minus 1, which would be -3 minus 1, which is -4. Oofda, that's a lot to plug in. So let's stick with that and see what this graph looks like. See if it does all the things we said it was going to. So what I did was I plotted -2, -1, -1, -2, 2, -3, and 7, -4. And then I connected from that first point all the way to the edge on the right-hand side. So notice it didn't really stretch it or compress it, so it's kind of the same shape as the parent function. It didn't get bigger or smaller, but it did reflect over the x-axis because it's upside down. It did move 2 units to the left, and it did in fact move down 1 from where it started. So that would be the sketch of that transformation. And I think that's going to be good enough for now. We'll finish that following function next time in class.